the announcement by the Gemini Observatory that the interstellar object 3I Atlas is not traveling alone but appears to have an escort has forced astronomers to rethink what they understand about visitors from beyond our solar system. What was once believed to be a solitary traveler now seems to have company. For an object arriving from outside our solar system on a hyperbolic trajectory, the discovery of a nearby companion overturns the simple image of a lone wanderer and opens up fascinating possibilities about how interstellar objects behave, how they are ejected from their home star systems, and how they interact with the solar environment. Before we continue, don't forget to like and subscribe for more updates. The object known as 3I Atlas was already extraordinary. It is only the third confirmed interstellar object to pass through our solar system and one of the fastest, following an extremely hyperbolic orbit that proves it is not gravitationally bound to the sun. Its discovery captured imaginations around the world, a visitor from another star system making a brief appearance at our cosmic doorstep. Yet, new Gemini images suggest that what we are seeing is not merely a solitary comet nucleus with its outgassing coma and dust tail, but rather a more complex system. The data hint at a companion, perhaps a fragment, a co-traveler, or even a captured satellite of sorts. This revelation immediately raises a series of urgent questions. How did this escort form? What does its presence reveal about the formation and structure of 3I Atlas? And what broader implications might it hold for our understanding of interstellar object dynamics? Imagine the scene. 3I Atlas hurtles through space toward the sun, surrounded by a faint cloud of gas and dust, trailing a luminous tail. Beside or just behind it, a smaller object keeps pace, a mysterious escort. Gemini's observations, which were originally focused on the comet's growing tail and its increasing brightness, now show faint hints of distinct points of light moving in unison with the main object. The primary nucleus dominates the brightness, and the coma's haze obscures a direct view of the solid body. Yet imaging sequences reveal subtle motion that cannot be explained as a background star or random artifact. If 3I Atlas is indeed accompanied, the implications are profound. One immediate theory is fragmentation. Perhaps 3I Atlas shed a piece of itself long ago, possibly during a close approach to its parent star, or as a result of internal stresses or volatile outbursts. And that fragment has continued to travel on a nearly identical path. If so, it means this interstellar visitor began to break apart before even entering our solar system, suggesting a much more dynamic past than a simple ejection and inert journey. Another possibility is that the escort is gravitationally bound to the main body, forming a binary or multiple component system. If true, this means interstellar objects might not always be solitary chunks of ice and rock, but sometimes complex systems traveling together. The presence of an escort also raises questions about the environment in which such bodies form. If 3I Atlas truly has a companion, it brings to mind the binary asteroids and paired objects we see within our own solar system. Perhaps the ejection mechanism in its original star system was violent, but managed to preserve both fragments as a pair. Alternatively, they could have formed close to one another around the same parent body and been ejected together. This would mean that interstellar comets may often be expelled in small groups rather than as single objects. The timing of Gemini's discovery is significant. 3. Atlas has already been displaying remarkable activity. Its tail has grown larger and brighter even before reaching perihelion, behaving more energetically than expected. Because its coma and dust tail are so expansive, the companion may have been obscured until now, hidden within the bright haze. As the comet approaches the sun, its environment becomes increasingly volatile, with dust streams, solar radiation, and solar wind all influencing its structure. The fact that the escort remains coherent and visible despite these forces suggests it is not just a loose clump of debris but a stable, enduring object. Astronomers will now closely monitor whether the companion maintains a consistent distance from the main nucleus, diverges, or fragments further. Its existence could profoundly affect how we understand interactions between interstellar bodies and the solar system. As 3. I-Atlas passes near Mars, swings close to the Sun, and eventually exits back into interstellar space. Tidal forces, radiation pressure, and planetary gravity will all act upon it. This event provides the first opportunity to study how a multi-body interstellar system behaves when exposed to the conditions inside another star system. Could the companion be stripped away? Could it evolve into an independent object orbiting within our solar system? Or will it provide new insights into how interstellar matter evolves under stellar influence? The discovery also forces astronomers to reconsider how they observe and interpret data about interstellar visitors. The first two confirmed interstellar objects, 1I Oumuamua and 2I Borisov, were assumed to be solitary travelers. If interstellar comets often carry companions or fragments, scientists may need to revisit archival images to see if smaller trailing bodies were previously missed. Future detection strategies might also shift to include searches for faint synchronized companions moving alongside main objects. The revelation from Gemini suggests that interstellar travelers may arrive not as lonely wanderers, but as members of small families. This finding is also a testament to modern observational technology. The Gemini Observatory, with its powerful mirrors and advanced imaging instruments, has enabled astronomers to detect subtle variations in light and motion that would have been invisible just a decade ago. The detection of an escort around 3I Atlas demonstrates how far our observational precision has come and how our tools now allow us to perceive minute details of objects millions of kilometers away. This capability opens the door to phenomena that challenge our long-held assumptions about comets and interstellar visitors. If the escort is gravitationally bound, its physical nature becomes an intriguing question. It could be a small fragment split off from the main body, either long ago due to internal pressure or more recently through outgassing. Alternatively, it could be a secondary object that was ejected together with the primary from its home system. If bound, its motion indicates that the main nucleus may be massive enough to maintain gravitational cohesion even after traveling across interstellar space. This in turn raises deeper questions about what kind of event in its parent system could eject both bodies together. Perhaps a close stellar flyby or the influence of a giant planet that launched them outward in tandem. It's also possible that the companion is not bound, but simply traveling close by on a similar trajectory, having separated earlier. In that case, what we are seeing could be part of a larger train of fragments, with 3I Atlas being just one of several pieces from a larger body. If so, the object is less a single nucleus and more a fragment swarm. This would imply that interstellar ejections often produce multiple small bodies rather than one large one, and we may only be seeing the brightest among them. The composition of 3I Atlas further deepens the intrigue. Observations indicate that it contains unusually high levels of carbon dioxide, as well as water ice and various volatiles, distinguishing it from most solar system comets. If both the main body and its companion can be studied independently, differences in dust production, coma structure, or tail morphology might reveal how the two separated and how they respond differently to solar heating. The presence of an escort could therefore serve as a natural experiment. Two related bodies, one slightly altered by time and distance, offering comparative data about interstellar materials. This development also increases the object's scientific value. Past discussions about sending spacecraft to interstellar visitors focused on single targets, but if multiple bodies travel together, the potential for comparative observation rises dramatically. Although a mission to 3I Atlas remains impractical due to its immense velocity, its dual nature gives scientists more incentive to study it in depth from Earth. 2. Bodies of shared origin but differing. Evolution present an unparalleled opportunity for understanding interstellar processes, interstellar objects, like 3I. Atlas are not merely curiosities, they are messengers from other suns, carrying chemical and physical evidence of worlds beyond our reach. When such an object arrives with an escort, the message it delivers becomes richer. Instead of a single data point, we gain a small system, a pair of bodies sharing a common past, but perhaps different fates. This discovery suggests that ejection processes from other star systems may often produce families of fragments, rather than lone wanderers. It also demands a reevaluation of previous data. Some features in the dust tail or coma of 3I Atlas that were attributed solely to its main nucleus may actually be influenced by the companion's activity. Perturbations in tail direction or irregular brightness variations could be signs of two interacting bodies. The path that 3I Atlas follows through the solar system, with its perihelion just inside Mars's orbit, ensures intense solar heating. If both objects remain intact through perihelion, their differing responses to solar stress could reveal much about how interstellar materials behave near a star. Gravita.